So ionization energies, if we go back to the notes, okay, over here, where it says ionization energy, okay, are really important for understanding how metals work. Hey guys, I'm recording and it's picking up all your sounds, so keep it to a minimum. Understanding how metals work. Okay? Alright, so what we talked about yesterday is that as you go left to right, if you're holding the electron really tightly because you have a lot of protons like neon does, in comparison to lithium, if you're holding the electron really tight, if someone was going to come from the outside to snatch my electron away, they'd have to spend a lot of energy over here, right, than they would over there. And I think the example I gave you was kind of like if you were walking down the street in the Bronx holding your purse, right? If you're holding your purse really tightly, close to your body, someone who's coming to rob you, right, a mugger would have to spend a lot more energy here to steal your purse from you than over there when you're holding the purse far away from your body. Okay? The actual numerical value for neon in terms of ionization energy is like 2,081 kilojoules per mole. And then for lithium, it was like 520. Okay? All right, so the closer you have that electron to the nucleus, the larger the ionization energy. You should recognize that the relationship is kind of inverse. The smaller the radius, the bigger the energy. As you go down the family, the ionization energy for potassium is something like 404 kilojoules per mole. All right, so what's happening here? We're getting smaller, right? Why is it taking less energy to steal that electron over here? Because it's much further away. And I think the analogy I gave you is if I was holding my purse but I was wearing 5 puffy coats, right? Why would it be easier for a mugger to steal my purse if I'm wearing 5 puffy coats? I got more layers. My arms are sticking out. I've got all these layers getting in the way, keeping me from being able to really effectively grab onto my purse. All right. What we're going to talk about next, electronegativity. This is how metals work. Electronegativity is how non-metals work. All right. This is how non-metals work. Okay, so electronegativity is actually not a number that's been measured in the lab. So ionization energy is an actual number that is determined from an experiment. Electronegativity is a BS number. This guy, Linus Pauling, made these numbers up. All right? And it's actually calculated from several atomic properties. And what the value tells you, remember what metals do? What do metals do? They give off electrons to become positive. What do non-metals do? They do the opposite, which is they take in. The value describes the tendency of an atom to gain electrons from other atoms. Basically, the higher the value, the more capable the atom is to attract an external electron. All right, so remember I was going around like an idiot with this little board with the magnets on it? Okay, all right, so I'm going to do it again. Okay, so here I am. Electron. I'm over here. Okay. What's wrong with me? What's wrong with me? You have 3. I have no electrons. Okay. I'd love to get some electrons, but there's another problem with me. I'm too far away. Yes. Right? First of all, protons attract electrons. They'll only stick when they're in close proximity. So I have to bump randomly around the universe and just hope that I come close to another electron. And if I do come close to an electron, it'll stick to me. All right? Now, is that enough electrons to satisfy this atom? No. So I would have to bump along and find another one. Okay? All right. Fantastic. I would move along, find another one. Okay? All right. Very good. I would love to get to you, right? There's a problem.
Not satisfied.
Well, I would love nothing more than to get that fourth electron, right? Because my outermost ring is not full, right? But I can't get to you. I'm not strong enough. I didn't eat my Wheaties, right? So I might not come and grab your electron for you. Okay? Now, what if I was a different element? What if I was this element? Would I have a greater chance of coming and claiming my electron?
Yes.
Okay. All right. So what was the difference here? 5 more protons. All right. So let's take a look at these elements here. In that, just going left and right across the period. Dominic, put your phone away, please, before I take it and write a referral and take your notes out. All right. So, first of all, what do atoms use? They're protons. What do they use them for? To attract what? Electrons from other atoms. Those electrons can go in that valence shell to complete it. Electrons are most easily attracted by nuclei with many protons. Provided what? Provided they're not being shielded or blocked by additional core shells. Remember yesterday we were here with a string? Yeah. And I was holding on to my electron. Who's my electron? You? Yeah. Okay. What if it was Caleb? Okay. So Caleb was my electron. You were the electron in the middle? No. The original. Okay. So I was holding on to my electron, but what happened when you put extra electrons in the middle? They pushed away. All right. So the more protons you have, the better it is for you to be able to pull electrons, provided you're not being blocked by other guys in the middle, right? Because other guys in the middle are going to fight against the nucleus and push away. All right, so remember how many protons lithium had? 3. How many does nitrogen have? 7. How many does neon have? 10. Let me cover this up for a moment because I just want you to focus just across the here. 3, 7, 10. It's the atomic number. So based on what we just learned here, who's capable of taking that electron and snatching it in the best? Neon. So I'm going to draw a big fat arrow here. Big fat arrow. What does the arrow represent? It's that pull inward, right? So the arrow represents the pulling force that the protons in the nucleus exert on the external electron. The wider the arrow, the stronger the force. Okay, so here the force pulling inward is going to be huge. How about over here in lithium? It's going to be tiny, so we'll draw like a thin one. A thin arrow. What about in the case of nitrogen? Kind of in the middle. All right, let me give you the values for electronegativity for lithium, nitrogen, neon. So lithium has a value of 1.0. Nitrogen has a value of 3.0. Oh, there's a problem with neon. Oh, there's no electronegativity given. All right, so first of all, why is the value bigger here for nitrogen? Because the force is stronger. It's better able to steal electrons from external environments. Why is it better suited for that? It has more protons, okay? What's going on with neon? All right, so even though the nucleus is perfectly suited for bringing electrons, that outermost shell is full. So it's not going to make a difference. This is a problem that neon has, helium, argon, krypton, xenon, and radon all have. Right? Noble gases do not have assigned electronegativity values because there's nowhere to put the electron. Okay? Even though, technically speaking, their nuclei are the best at grabbing the electrons. They just can't, there's nowhere they can go. All right? And that's explained here. It says noble gases don't have assigned electronegativity values. While they possess large numbers of protons in a small radius, which would normally be good for attracting electrons, their valence shell does not have room for additional electrons. So it's down here, right, in the second italicized paragraph. You want to fill that in with room. Okay? Yes, sir.
Can you make a noble gas an ion?
Can you make a noble gas an ion? It takes a lot of energy. Excuse me. Johnny. Hi. That's fine. Thank you. See you. Bye. All right. Let's take a look down the family. Okay? Down the family. And let me give you the values here. So the electronegativity value for sodium is 0.9. For potassium is 0.8. So if I had to draw arrows, this arrow here would be a little thinner than the one above it. Right? And then the one at the bottom would be like a really thin arrow, right? Super thin arrow. How come? What's happening as we go down the family? What are we doing? We're adding shields, right? So in this first case, we had one layer in the middle pushing out. In the second case, we have 2 layers pushing out. And in the third case, we have 3 layers pushing out. The more layers are pushing out, right, the less effective the nucleus is. It can't do its job. All right, so let's fill out this bold at the bottom. And I think we should start with the bottom sentence first, the one that says the smallest electronegativity. All right, so where's the smaller number? On the left or on the right? Left. Top or bottom? So the smallest electronegativity values are on the bottom left. Give me the element. It'll be francium. Okay, let's do the other one, the one above. This one's a little bit tougher. Okay, where are the largest electronegativity values? Top, right. Give me an element. Okay, well, the one that's in the top right on the periodic table is helium, but what did I just tell you about the noble gases? They don't have electronegativities at all. So the next best choice is fluorine. Okay? All right, I'm going to turn the camera off. Let me just do that.